So now we'll move on to the second talk of the day. We'll have Rongchan Zhu, who will be speaking about the large N limit and 1/n expansion of the observables for the ON linear sigma model via SPDE.
Okay, can you say something?
Yeah.
Okay, great.
Okay. Maybe I put it here. Is okay. Okay, this is we'll first go to introduction part. In this talk, we will concentrate on this ON linear sigma model, and in this case, it's phi the vector model. And depending on this, we have a parameter n here. This is a big capital N here, and here for the linear part, just given by this product measure of this Gaussian free field. And here we also have this nonlinear interaction part. Okay, so this is denoted in this real terms comes from here. And here for when n equals to 1, this is just this 5,4D model from quantum field theory. And here we are interested in this large N limit behavior of this kind of model. And here for this kind of, to study this large N limit is, this ON model is a complicated model. If we study the large N limit, when n goes to infinity, we may get some simplified model, which can be used to approximate this large N limit behavior of this OM linear sigma model. And for this larger limit behavior of this quantum field theory, this has been studied a lot in the physical and mathematical literatures. For the physics result, this first has been studied by Stanley for spin glass, and later by this Wilson to also propose this OM model and studying the larger limit behavior. And also by this Gross and Hopf to study this larger limit of this other quantum fields. For example, Hopf has studied this larger limit for this Yang-Mills model, and in their case, they can get some when they calculate some physical quantities, they find when they calculate the larger limit, there's some simplifications. And for the mathematical result, the first result maybe comes from this Kupiani, to the best of our knowledge. He has done this 1/n expansions for this for the log of the partition functions of these ON models here. And in his approach, he uses a dual representation for this quantum fields for this ON model. And later, this result has been extended by these two guys, this Billy, these two guys, and they studied this 1/n expansions for the Schwinger functions. And more recently, this Ferdinandi and others also using this, also study this 1/n expansion for the related Schwinger functions by using this loop vertex expansions. And also for this Yang-Mills model, this Harry Levy, they also studied the larger limit behavior of the Wilson loop. And also this Chatterjee has studied the behavior of the larger limit behavior of the Wilson loop for the lattice Yang-Mills model. And in this talk, we were using this SPDE, using the stochastic quantization to study the larger limit of this ON linear sigma model. And in this case, our SPDE is we consider on the 2-dimensional or 3-dimensional torus. three-dimensional torus, and the linear operators also comes from this Gaussian free field, and the nonlinear interaction comes from taking partial derivative for this rate nonlinear interactions. And we also have independent space-wide noise to driven this noise. Before proceeding, we first recall our previous result on the larger limit for this dynamics. For this kind of dynamics, due to the driven noise, is this space-time white noise. So this case, to understand nonlinearity, we also need to using this renormalization. And in this case, we use this Wick renormalization. So this is our nonlinear SPDEs. And in this case, for this nonlinear SPDE, this nonlinear part, we have this average of this 5J square. So this reminds us this law of large numbers. So we could guess the limit should given by some we can guess the limit should given by some expectation of this 5J square to replace this average of this 5J square part. So we guess the limiting equation should be written in the following way. So we keep this linear part and the nonlinearity part, this one. This average by using this law of large number should go to this one. But here we cannot use law of large number since this 5J for each component, they are not independent. But when n goes to large for different component, their interaction should become weaker because here this is 1 over n. So this also reminds us we can still expect this should be true. So we can prove this result for 2D case. If the initial data of this limiting equation are independent, and they share the same law. And if the initial data of this phi I were convergence to the initial data of the limiting equation, then we can get, and for fixed time t, this phi I will convergence to this limiting this equation, the solution of this dynamics. And we can also obtain the convergence and stochastic process, but the convergence is only converge in probability. This kind of result is like a mean field limit result, also called this propagation of chaos result. So that means if we starting from this, we just look this dynamic as a particle system, and starting from this initial data, this phi I, even this phi I equals to this psi I, so initial data, they are independent. But for fixed, if we involve this phi I using this dynamics, and for fixed time t, they are not independent because now here they have interactions to each other. But if we let the number of the particles goes to infinity, now they becomes independent. Here for the limiting equation, it's only depending on the law of the solution itself. It will not depending on other component. So for different components, they are independent. So this is the convergence of the dynamics. And we want to using the convergence of the dynamics to study the convergence of the environment layers. It is expected the related field should converge. For the dynamic, for this first nonlinear equations, we can see the related invariant measure just given by this ON linear sigma model. So it's expected the invariant measure, this ON linear sigma model should converge to the invariant measure to this limiting equations. And to analyze the invariant measure for the limiting equations, in this case, we consider for this is quantum field, and this psi should satisfy the shifting invariance property. So the expectation of it should be just a constant. So this is a constant. So this just gives us a linear equation. We could write this invariant measure explicitly, directly. This is just given by a Gaussian field. And due to the effect of renormalization, we could see the Gaussian free field is the invariant measure for this limiting equations. So before we also can obtain the convergence of the dynamics both in 2D and 3D case. We consider for the ice component of this ON model. First, they form a tight set in suitable Basel space. For 2D, it's just say minus kappa space. For 3D, it's in our space. But here to identify limit, we still need this m is bigger than m0. Until now, we don't know how to drop this condition. And we could prove this new ni will convergence to this Gaussian free field. And also the first k component will convergence to this product measure. This is like to say this measure is asymptotic independent because this product measure corresponding to the random variable, they are independent. And we also have the following convergence rate with respect to suitable Wasserstein distance. And the convergence rate is given, it can be controlled by n to the power minus 1/2. This convergence rate seems to be optimal convergence rate. We can compare these two measures. And here, if we consider this result to understand intuitively, we see these nonlinear interactions for this part. Here, for these nonlinear interactions, we also have Wick renormalization. And if we just overlook one square here, we just overlook this one square and consider average of this phi j square part. And this also reminds us this law of large numbers in this Hamiltonian part. So this part should just goes to the expectation of this phi j square formally. And due to the effect of the renormalization, the expectation of this phi j square is 0. So this part will disappear when we see the larger limit of this model. We didn't see any non-trivial interactions for this from this nonlinearity. When we consider this larger limit. So in this case, we want to see whether we could choose other here we just take a look at the larger limit of the field. So in this case, we didn't see any non-trivial interactions. We just see still gives by this Gaussian free field. But if we consider whether we can choose other observables, which also satisfy this ON symmetry property, can we see some other non-trivial effect? So in the second part of my talk is about this larger limit of these observables. And formally, as I just mentioned before, if we consider this phi I is distributed as this ON model, so if we consider average of it, this is just the scale for this law of large numbers. So this will goes to 0 due to the this Wick renormalization. But now this is goes to 0, so it's like this scaling for this law of large number is this n is too big. So now we want to change the scaling from this scaling for law of large number to the central limit theory. So here we change this 1/n to this 1/square root of n, and we consider these observables. And here we also consider the nth power of this kind of observables, and with suitable Wick renormalization here. And we want to see the larger limit of these observables. Formally, if we consider to prove the convergence of the field, we construct a coupling to prove the convergence of the field by using the stochastic quantization. So this phi I could be seen as the invariant measure for this stationary solution to the stochastic quantization, and Zi is also stochastic quantization for the stochastic heat equation. And using this coupling, we could prove this phi I will convergence to this Zi, and Zi is independent Gaussian free field. So it's natural to ask, when we take larger limit for the observables, can we also get the same result? Just replace each phi by this Zi here, just replace it to this Gaussian free field, and they are independent. In this case, on the right-hand side, they are independent and mean zero. So it's easy to use in this central limit theory. And to say it's also the larger limit, the law of it is a Gaussian field with mean zero. And the correlation function is 2c squared. This c is just equals to the green function of this m minus Laplacian operator. So this is our Gaussian field. So this is our first question. It's also natural to ask for the nth power of this observables for this kind of observable. Is this limit the same as the nth power of this z here? This is our question, and our first result is to see the larger limit of this kind of observables. And we could first determine the law of this larger limit of these observables. Here to introduce our results, we first using this shorthand notation, this phi square. We use it to denote this the sum of this phi square part. And we take this nth power also using this Wick product. And in the following of the talk, we always assume this dimension d is equal to 2. And m should be larger than m0. And in this case, we could obtain this first observables were convergence in law in this H minus kappa space. And the limit is the mean zero Gaussian field with the correlation function will determined by this green function of this Gaussian field, or green function of this Gaussian field here. And here we can see for this nonlinear part, for this covariance function G, compare before for this Z part, the correlation is just 2c squared. So the difference from here is we have c squared to convolution with this G. So where this term comes from? This term just comes from the interaction between this first observables with this nonlinear interactions. So this will give us say and do this convolution to have this new correlation function G here. And we also can calculate the law of the second observable, just choosing n equals to 2. And they also convergence in law to the following, to the square of this Q. And now if we calculate the regularity of this Q pathwisely, and we see here the correlation function given by this G, and the main singular part for this G comes from this 2c squared. It's also singular at the origin. So it's like some log correlated by log square correlated field. So in this case, the regularity for this Q we can get is also in C minus kappa space. So to define this Q square, it's also not well defined in the classical sense, but it's a Gaussian field. We could using this Wick renormalization to redefine it. For example, we could choosing this G0 as our Wick renormalization constant to redefine this Q square. But here, the limit of this second observable does not converge to this Q square, but it converges to another Q square, which is Wick renormalized by using this renormalization constant, this 2c square part here. Here, to see here, this 2c square, this term, this renormalization constant just comes from if we just replace this phi I by the larger limit. So if we want to define this z square part, the renormalization constant is this 2c square. So this means this renormalization will not be influenced by the nonlinear interaction, but we just replace this phi I by this zi. So we still get this is the limit, but the correlation function of the first observables will influenced by this by this nonlinear interactions. And here we just write it in the limit in this way, and we could also denote this Wick this Q square part, but with renormalization constant by the usual Wick this Q square part, but with another additional constant. This additional constant just comes from the compare this 2c square 0 and g0. So we get, but this constant is a finite constant. Here it can be written in this way. And we can also consider higher order case. For general n, if n is just a vector, we could calculate, we could also calculate the limiting joint law of all these observables. We could prove all this joint law of these observables were convergence, were convergence to this convergence to this Qn, but with the also with suitable renormalization. But here the renormalization constant is still this 2c square 0 part, not given by this g0 here. And here this Hn is this Hermite polynomial. This is the usual definition for the Wick product. But here we just change the renormalization constant in this way. And this is our first main result for this larger limit of these observables. And to derive this result in the following, I will talk about how we obtain this kind of a result by using SPDE. So our first step is to using this stochastic quantization using this SPDE. And we just recall our stochastic quantization equation in this way. And each psi are independent. And by using this SPDE, we could get the following uniform estimates for the stationary solutions to this stochastic quantization equations. This means for any L and any so for any Wick, so for any this this nth order of this observables, we could calculate the L's power of it. And here we need to calculate the H minus kappa norm of it, and it can be controlled by the n to the power NL to NL over 2 can be controlled by this one. And also this kind of estimate gives us first the right scaling for each observables, because from here we already see each observables are tight and we can see their larger limit. And to understand this result, if we just simply choose n equal to 1 and write it using this you will take this called this Daprato and Debush trick to understand this stochastic quantization equation to decompose this phi I to this Zi and plus this Yi part. Zi will be the Gaussian free field part and Yi will satisfy a nonlinear equation. If we substitute this one into this phi square part, we will write it in the following one. And in this case, we have n terms to take summation. But the important thing is here we calculate we first calculate their norm in a Hilbert space and taking the inner product. We're using the inner product and taking the expectation and consider for this Zi part, this renormalization part, this mean 0. So if we just calculate the H minus kappa norm of it, we could say this sum just gives us, we could say one square root of n. So the order of it is of order square root of n. And we could extend this from this Zi square part to this also for this phi part by using SPDE estimate. And for the second uniform, this estimate will also help us to identify limit. When we to derive the convergence in law result, we were using the integration by parts formula, and we will get a lot of error part. And this kind of estimate, it's like the power counting part. This gives us each phi square is of order square root of n. But if we just need to calculate to count how many how much numbers of this phi square for each term we have, so we could determine the order of each terms. And to technically speaking, to derive this kind of estimate with using some mean field type estimate, first to consider the L2 norm estimate for this yi, and also, but this is not enough to obtain such kind of higher order moment estimate. So this we also need to do the LP norm estimate for yi, but it's depending on n. But finally, by combined with the shorter estimate, this gives us the correct estimate here. And the second ingredient of our proof is this Dyson-Schwinger equations, which has been used a lot in this quantum field theory. This is just like an integration by parts formula. Now, if we choose a test function f, and take a partial derivative with respect to this phi 1 here. And on the right hand side, we're using this integration by parts. This partial derivative should go to the Mayer. And by using the density of the Mayer, this first part, m sub minus this Laplacian part, comes from the comes from this Gaussian free field, and the last part comes from this nonlinearity. And for this integration by parts formula, we could using the m minus Laplace inverse of it to on the both sides of the equations, we could get the following kind of equations here. And the advantage of this kind of integration by parts formula is we could choose suitable test functions to get the correlation relations for this kind of field. For example, if we just take this f phi equals to this phi 1 y at some point y, so this part just gives us the correlation functions for this phi 1. And the left-hand side is just the green function of the Gaussian. So this gives us the relation between this green function of this phi and the green function of this Gaussian free field. And here, this part I just mentioned, this phi square is only involves one phi square. So the order of it is of square root of n. So the whole order of this term is 1 over square root of n. So it's like an arrow part. And we could do more. For example, if we want to analyze the 2-point functions of the first observables, we just choosing this kind of test functions and choosing this x equals to y1. And for example, by taking partial derivatives here, we could get, if we taking partial derivatives for these observables, we get this phi 1 y2 here. And we also get this cy1 minus y2. This is the green function of the Gaussian part. But on the right-hand side, by observe the renormalization part, we will get this part is the correlation functions of 1 over 1 of the correlation functions of this first observables. Yeah, and the second and the last terms is like some comes from this nonlinearity. In this case, if we do this integration by parts once again, for the first part, we could replace this first correlation by the green function of the Gaussian. And for the last terms, we could also replace this 2 phi 1 by also the green function of this Gaussian. So this finally gives us the following equations for this G part here. We get this G is the larger limit of these correlation functions. So they just satisfy these equations for this G here. And we could do more if we consider the K point functions. And we could also using this integration by parts formula to obtain the following recursive relations. This means on the left-hand side, we have this Fk, this is K correlation functions. And we also add another terms. This is do this convolution with this C square. This is from this nonlinear interaction. from this Gaussian, from this nonlinear terms. And we also have this phi k the k minus 2 point functions, and the interaction comes from this y1, the point y1 to this yj pattern. And this recursive relation should we could say the solution to it should be unique. And for k equal to 2, we already know this f2 equals to g. And for general fk, we could find the solution to these equations. This fk could be denoted as this product of this f2. And here this pi just runs all these pairing permutations. Here, to derive this results, when we try this, we have this guess to say this fk could be denoted this one, and we substitute this formula into this equation, and we find this fk will satisfy these equations, and this relation will implies this the larger limit of this first observables is the Gaussian functions, because for the Gaussian functions the correlation satisfy this kind of relations, the k-point function could be determined by these 2-point functions. And for more general case, we also find some general recursive relations. For example, if we consider this n is the vectors for this general observables, we could derive the following general recursive relations. For example, if this fnk is just the k-point functions of this nth observables, and the second term also comes from the interaction between this first observable, just this phi square, this y1, and the interaction with this nonlinear terms. And also on the right-hand side, we would get the following correlation functions. And this correlation functions, it represents this the interaction between this the observables and point y1 and the observables and point yj. And this recursive relation, we could also say the solution for it should also be unique. And the idea for it is also we find the explicit solution for this recursive relation. And we could denote it as the solution to the we could denote the solution as the k-point functions of this q to the power n, but with this suitable renormalization constant from this 2c square. So this gives us this larger limit, the larger limit result. This is the first result we mentioned. And the second result is about this 1/1 expansions. And in our case, we could say all these other observables, the main behavior comes from the first observables, just choosing this n equals to 1. To understand better about the behaviors, we could consider this 1/1 expansions for this k-correlation functions for this first observables. And we could obtain the following 1/1 expansion result for any p is for any integer or for any natural numbers. We have the following asymptotic expansions around the around this 1/n. So if k is even, we have the following expansions. Fk here, and on the right hand side, this capital Fn k is independent of this capital N and only depending on the Green function of the Gaussian free field. And the remainder term, this R part, we could control them uniformly in H minus kappa norm, and we could bound it by a constant. And if k is just odd, we have this kind of 1/1 expansions. So this means we have extra square root of n here. To understand this, if we just do some formal expansions to write the observables and the expectation as the exponential with the related Hamiltonian and do formal expansions, we could say if k is odd, here we get extra square root of n here. So this explains also our result here. We have this extra square root of n here. So this is our second result for this expansion, one-over-n expansion. To understand this, to prove this results, we also still our tool is also this uniform estimate from SPDE, and the second tool is also from this integration by parts formula. And to use this, we need to introduce some graph notations. For example, for this integration by parts formula, we also recall it here. And we will use this C by a line. This is to denote it by a line. And we also use some single, double or triple this wavelengths to represent this stochastic object like phi1 and phi2 and phi cubic part. But here we will have extra this 1 over square root n here. So this part should be of order 1, and this part is of order 1. For example, if we consider the 4-point functions of this observables, we just represent this recursive relations here. It's like we here on the left we have this convolution with this six square. This part will denote this convolution with this six square, and on the right it will have the interaction between this point and with other points. So we get this kind of graph, and this part is of order 1 over square root of n by using this SPDE estimate. And here to handle the left-hand side, we were using this operator K here. This is identity plus this, do this convolution with this C square. To apply this operator on the both sides, we could write the tape of this 4-point functions in the following way. This is just connect to a blue line. Now we could use this graph notation to obtain the 1 over n expansions, but the idea of the proof is we still need to using this integration by parts formula. And here we will find if we could for the integration by parts formula we could choose different test functions, but in our case we only need 2 types of integration by parts formulas. The first type is just for this observables. And this is like our recursive relation, and the right-hand side is just connect to 2 points of it. And other terms should be of order of 1 over square root of n. And but the remainder terms is remainder term, all the form of the remainder terms only evolves to this phi1 phi square part. So if we just apply this integration by parts again for it, this is only just replace this phi1 phi1 by a line cx1 minus x2, and the arrow terms will have the same form as this one, as this. The second part. So this gives us 2 types of these graphs, also 2 types of this integration by parts formula. And if we repeat this integration by parts formula each time, we find that we will reduce the number of this phi square. So finally, this will give us find the functions f, this fn here. But the remainder term is only of this 1 over square root of n. So this only gives us this 1 over square root of n expansions. This is argument is similar as our previous work for this asymptotic expansion for this 542 model. But how to get more to get this 1 over n expansion by using this argument? We need to analyze the parity of this, or just like this evenness or oddness of the number of this phi square. We find that when we use this integration by parts procedure for each time, we reduce the number of phi square by 2. So this will not change the parity of this, the number of this phi square. And finally, if an odd graph can be reduced to the following kind of terms, we already know this phi square part is of order 1, or if is of order square root of n. But if we calculate the expectation of it is of order 1. So this will give us each odd graph is of order 1 over square root of m. And if we substitute this one, this gives us this 1 over 1 expansions. This is the main idea how we get this 1 over 1 expansion. But the other thing we need to do is here this helps us to find this Fn, we call this result. But find this Fn, but we also have this remainder part. This remainder part also depending on each phi I, depending on these phi's, depending on all these observables. So it's also depending on n. And the remainder thing we need to do is to prove this each remainder part should be of order 1. To obtain this, we're also using this graph notation. So this is how to estimate each of these graphs. And to do this, we just analyze this integration by parts formula. We get 2 new C here from this integration by parts. On the left-hand side, this is by taking partial derivatives, and we reduce the number of this phi. And on the right-hand side, we get a new this phi square. But in this case, we have this 1 over m. This gives us C. So we will using the green color for the left-hand side, and using the red color for this for the right-hand side for this C here. And K is the blue line. And the idea now is we want to prove this graph is of order 1. By using SPD estimate, we already know each this wavy line is of order 1. But this graph seems more complicated. But the idea is we cut each this green line by replace them by the independent Gaussian free field. And we could still using SPD to see each this small this wavy lines is bounded by a constant independent of m, and by using induction estimate, we can estimate them from these leaves and go it here until it go to this U1. And finally, we get this is like a tree, we could get it is of order 1. So for each graph, we're using this induction estimate to obtain the remainder term is also of order 1. This is our second results. The last part is about this next order SPDE. Recall our main results is to using SPDE to derive this kind of results. And for the mean field limit of SPDE, we get distribution dependent SPDE. And we want to see whether we can see next order SPDEs. But if we just consider in the non-equilibrium case, we find there are some terms cannot be denoted by the equation. Maybe in this case, we need to consider in some empirical measures. So instead, we just consider the stationary case and compare this to, for this, first, this OM model, we just recall this is our stochastic quantization equations. And the Gaussian free field, we just recall the stochastic quantization is this stochastic heat equations. And we consider in the stationary setting, we want to analyze the fluctuation of this each component, this phi I minus this AI part. But we find the limit, they will satisfy the following limiting equations. It's a linear equation. And this PI comes from this nonlinearity part. Here we can prove they are stationary process. And we could also determine the time marginal distribution of it. It's determined also by this marginal limit of this first observables and the product with this independent Gaussian free field. This is, we could calculate it. The idea to calculate the law of it is also similar by using this integration by parts and also this SPD estimate. This is the main results of my talk. And for the last part, maybe I just mentioned some further questions. Here we only mention the two-dimensional case for the Lagrange limit of this observables. But for the For the three-dimensional case, we already know the tightness of this first observables, but how to identify the law of it, we still don't know, because here it seems we could still using this argument, but in 3D, uniform estimate until now is for this OR model is not strong enough to prove finally the remainder term should be of order 1. And also when we apply this integration by parts formula, this approach for three-dimensional case, there might be some new renormalization part will appear. Yeah, this makes this things more complicated in this case. And it's also interesting to study the larger problem for other models. Okay, thanks. Oh, thank you.